Welcome to lecture 10 of module 4. In this lecture, we are going to discuss on approximate analysis in boundary layer. In last lecture, what we have seen is we have found out that momentum integral equation and energy integral equations that we have developed, and these integral equations are used to find out to analyze the heat transfer behavior as well as momentum transport behavior in a boundary layer. So, we will see in this lecture through some analysis that how the heat transfer behavior and momentum transport behavior takes place. And for that, as we know already we have discussed, as because in this momentum integral analysis or energy integral analysis, we usually use a velocity profile that is assumed, and therefore, this analysis is called approximate analysis. So, what we will do is first we will start with momentum integral analysis. So, the momentum analysis. Momentum transport analysis rather. So, for that, what we know, our momentum integral equation is that already we have discussed in the last class. That is d dx of integral 0 to delta. Delta is the boundary layer thickness at any point x, v infinity minus Vx. Vx is the x directional velocity and v infinity is the free stream velocity along x direction, already we have discussed in the last class, into rho into Vx. Rho is the density of the fluid, and dy, and that is equal to say tau w. This is what the equation we have developed, and as we discussed that in this we have to have a velocity expressions to get some information about the wall shear stress, and that velocity expressions will assume to be, already we have discussed in the last class that one important way of getting a velocity profile we have discussed, and very well known and common velocity profile, nonlinear velocity profile, which is like of this form: Vx by infinity equal to 3 by 2 y by delta minus half y by delta whole cube. This we have discussed in the last lecture how to get this. And now, if we try to see tau w, that is equal to again mu into del Vx by del y at y equal to 0. So, this is Newton law of viscosity, tau mu into del Vx by del y, and tau w is the wall shear stress. So, this wall shear stress is happening at y equal to 0. So, if we just do this here, then what we will get is that this implies del Vx by del x, del Vx by del y, 1 by V infinity del Vx by del y is equal to 3 by 2 into 1 by delta minus 3 by 2 into y square by delta cube. So, that is coming from this equation, okay. And then from there we can write, so this implies that del Vx by del y at y equals to 0, and this is equal to 3 by 2 V infinity by delta, and the other term is 0. So, therefore, this is becoming 3 by 2 mu into V infinity by delta, that is the tau w. So, now, if I put it in, say, if I say it to be equation 1, in equation substituting in equation 1, what we can get is that V infinity square d dx of 0 to delta 1 minus Vx by V infinity into Vx by V infinity, because we know that our velocity term is in the form of Vx by V infinity. So, therefore, we are dividing by V infinity, which is just to get this expression into dy, and that is equal to the tau w is replaced by 3 mu V infinity by 2 rho into delta. That is what we have seen in the last derivations. So, okay. Now, there will be a rho here. So, because rho is been taken to this side, therefore, this rho has come to this side. Okay. Now, so or V infinity square into d dx of, if I now make say eta equal to 0 to 1 and the eta is y by delta. This is what already we have discussed, that we are defining a variable eta is equal to y by delta, and then it is becoming delta into 1 minus 3 by 2 eta plus half eta cube into 3 by 2 eta minus half eta cube into d eta. Okay. This delta term is becoming coming because of that, because we know that d eta, delta into d eta is becoming dy. So, dy is replaced by delta into d eta, and therefore, the delta term comes into picture over here, and this is becoming equal to 3 mu V infinity by 2 rho into delta. Okay. Now, after integration and putting the limit, after integration and putting the limits 0 to 1, we get the expressions that 39 by 280 V infinity square d delta by dx equals to mu into 3 mu V infinity by 2 rho into delta. As you can understand that d delta by dx, because we know that delta is a function of x. So, as we go along the plate, flat plate, that delta value, boundary layer thickness goes on increasing. Okay. Then, if we do further integration here to get the expression of delta versus x, so further integration, this integration is, then we can say delta, if I take this is delta into d delta, and this will be for 0 to delta, okay, and this is equal to 140 by 13. So, this cancels 3 into 3, 13, 39, 142. So, 140 by 13 mu by rho into V infinity into dx, and this range will be equal to x equal to 0 to x equal to x. So, at x equal to 0, delta equal to 0, and at x equal to x, delta is equal to delta. Okay. So, based on that, if we do the integration, then what we get is that half of delta square, that is becoming 140 by 13 mu x by rho into V infinity. So, this finally gives us that delta is equal to 280 by 13 into mu into x by rho into V infinity whole to the power half. Okay. And now, if we do this, we can get it, this is equal to 4.64 x by just little bit of rearrangement x V infinity by nu, and we know V infinity by nu is equal to nothing but Reynolds x. So, we will write it to be 4.64 into x by root over of Rex, and Rex is the local Reynolds number. So, therefore, we can write that delta by x, dimensionless thickness, dimensionless boundary layer thickness delta by x, this is equal to 4.64 into Rex to the power minus half. Okay. And if you remember that we have already analyzed a couple of lectures before, that for exact solution, this delta by x is actually 5.0 into Rex to the power minus half. So, we can see that there are slight or little variation between these two analyses, and this from exact solution we get delta boundary layer thickness as 5.0 into 10 to the power minus half, whereas in case of approximate analysis, understanding that or assuming the velocity profile, the value happens to be 4.64 to the power minus half. And then in the boundary layer, we have some more things for hydrodynamic analysis, some more things to be done, that is the tau wall, walls here, tau wall is equal to, that is equal to 3 into mu into V infinity by 2 delta, and this is equal to 0.323 rho V infinity square into Rex to the power minus half. Okay. And this we have got for exact, already we have seen it for exact solution, and this exact solution based on Blasius solution, I should say, is the Blasius solution. This is also Blasius solution. There tau w is equal to, we have got little bit different, it is 0.332 into rho V infinity square into Rex to the power minus half. Okay. And then two more things, like we have got FD, drag coefficient, that is total drag per unit width of the plate, that is equal to, we will get as 0 to L tau w into dx, and this will be 0.646 mu V infinity REL to the power minus half. So, REL is the Reynolds number based on the length of the plate, and by exact analysis we got this value to be FD is equal to 0.664, just little difference, mu into V infinity into REL to the power minus half, and we should write that REL, we should remember again, it is nothing but L V infinity by nu. Okay. And we know that Rex is equal to x V infinity by nu. Okay. That is the when it flows over a flat plate. Now, another part, that is the CD, is the skin drag coefficient or wall drag coefficient, whatever you say, skin drag coefficient. So, this drag coefficient is defined as the shear force divided by, that is the force on the skin, shear force divided by the inertial force is divided as shear force divided by inertial force, and we know that shear force is divided by inertial force, and this is equal to total shear force 0 to L tau w into dx into 1 is the force divided by rho V infinity square by 2. This is what, and this value is coming to be 1.292 Reynolds L to the power minus half. Okay. And according by exact analysis we got this value to be CD is equal to we got 1.328 into REL to the power minus half. So, what we can find is that using the approximate analysis, we are reaching very close to the predictions, to the estimations by exact analysis. So, therefore, approximate analysis, it is though it is simple, though it is giving you little bit of approximation, it is very simple, but it is considerably accurate, so that one can instead of going for exact analysis can go for approximate analysis to find out the behavior of fluid flow behavior, momentum transport behavior. As of now, what we have seen is the momentum transport behavior, then wall shear stress, all these things in turbulent in the boundary layer flow they can find out. Now, one thing also you have understood that the values of these values, whatever you have got, delta by Ax, CFAx, FD and all these things, tau w, all these things is dependent on the velocity profile we have assumed. We have assumed a particular velocity profile, but there can be a different type of velocity profile one can assume, and then if that happens, then what happens to the changes? This I will just give you a figure, a table. This table will give an idea that how or to what extent this varies, the estimations varies from the exact solution. So, if I make the table of this very quickly, it is like this. Okay. we will say that this is Vx by V infinity, and that is equal to say f of eta, and eta is equal to y by delta. So, we will write at f of y by delta, and this another part we will write as A is the constant, that is the delta by x into Re x to the power half. So, we have seen that delta by x is equal to some constant into Re x to the power minus, or just we are trying to see this constant, how much it comes, and the other case the B, this is another constant is with respect to CD into Re x to the power half. We have seen that both the cases, if we take the different velocity profile, the functionality remains the same with Reynolds number, which is Reynolds number to the power half, but the constant value does change, and we will see that how does it change. So, f eta first case is equal to eta. So, it is a linear profile in the boundary layer, linear velocity profile, and this becomes 3.46, it's wide 0.577, and then f eta is equal to say 2 eta. It is now a parabolic profile, it is 5.48, and this is 0.730. Then f eta equals to 3 by 2, this is what we have discussed just now, it is 4.64 and 0.647. Then f eta is equal to another, it is a long 4 degree polynomial, 2 eta minus 2 eta cube plus eta to the power 4. Here it is 5.84 and 0.685. Then f eta is a sinusoidal function, is equal to sine of pi by 2 into eta. Okay, this gives 4.80 and 0.654, and the other one is the final one. It is just to compare it with exact solution. Exact solution, that is 5.0 and 0.664. So, one thing we can see that this 4.64, 5.48 and 5.84, okay, these are very and 4.80, these are very close to the exact solution, and even in terms of this CD, if we see that this is also very close, this is also quite close, but this is little apart. But one thing we can say, so therefore this is this polynomial, that is 3 by 2 f eta is equal to 3 by 2 eta minus half eta cube. This happens to be more widely acceptable velocity profile in laminar boundary layer, but one may think of having some other kind of velocity profile and also can find out the values of A and B. Okay. So, this exercise can be done even to find out these values. Okay. Now, this is about that hydrodynamic boundary layer and about that in the laminar flow region, because the equation we have used is the laminar flow region. Now, exactly the similar kind of equation if we use for turbulent flow, we know the turbulent flow situation. So, if we consider the turbulent flow, we know, as I was telling, that we know the turbulent flow situation can be very nicely being explained in terms of a power law equation or 1/7 power equation. One-seventh power equation that is that Vx by V infinity, and that is equal to y by delta whole to the power 1 by 7. This 1/7 power law model also it is called 1/7 power law model, and it happens that that in case of turbulent flow, as we know that there is this laminar sublayer, and this sublayer laminar sublayer is very small. Now, if we just try to use this velocity profile in the momentum integral equation, but only thing is that there is a difficulty of getting tau w. So, getting a tau w is a difficulty, and we cannot just write like this as we have Newton's law of viscosity. From this equation if I say that this is equation 2, from equation 2 we can't find out tau w, that is not possible. Okay. The reason we can understand, if we say that del Vx by del y, it will be something will come this, and at y equal to 0 it will be, this function will be the del Vx by del y function, which will be a function of y, and it will remain undefined when y equals to 0. So, therefore, we cannot do this. So, what we have to do in case of turbulent flow analysis, we have to take an expression for tau w. So, let us tau w is taken to be like this, is equal to C d into rho v infinity square by 2, and that is equal to 0.0296 into nu by v infinity into x whole to the power 1 by 5 into rho v infinity square. So, this is the expression of tau w, this we have to use, and this is valid for a Reynolds number less than 10 to the power 7. So, so for a quite a very high value of Reynolds number turbulence, this tau w expression is applicable. So, what we can do is, we can use this velocity profile in the momentum integral equation. That is what we will write now. D dx of, our momentum integral equation is d dx of V a infinity 0 to delta V infinity minus Vx into Vx into rho into dy is equal to tau w. So, this I was writing as V infinity square d dx of 0 to delta 1 minus Vx by V infinity into Vx by V infinity, okay, into dy is equal to tau w by rho. So, now we will put that expression for Vx by infinity, and then we get d dx of 0 to delta 1 minus y by delta whole to the power 1 by 7, okay, into y by delta whole to the power 1 by 7 into dy, and that happens to be 0.0296. If we put the value of tau w over here, nu by v infinity into x whole to the power 1 by 5, and from there if we do the integration, after integrating, so we get that d delta by dx is equal to 72 by 7 into 0.0296 into nu by v infinity whole to the power 1 by 5 x to the power minus 1 by 5, and then again this integration of case 1, that boundary layer is turbulent from leading edge itself, from the leading edge itself, that is delta equals to 0 when x equal to 0, and so in the end we will get delta by x is equal to 0.381 into Rex to the power minus 1 by 5, and case 2, but boundary layer is laminar, up to the critical Reynolds number REC, and that is equal to 5 into 10 to the power 5, okay, and turbulent thereafter. Okay. Then what we have, the integration can be from delta lam to delta. So, we can have, and under this situation delta is equal to delta laminar, which is at x critical, and that is equal to 5 into 10 to the power 5 into nu by v infinity nu by V infinity, and delta laminar basically is equal to 5.0 into x critical from the exact analysis, 5 into 10 to the power 5 whole to the power minus half. This is from exact analysis. And then what we get is, if we do the integration, delta minus delta laminar becomes 0.381 nu by V infinity whole to the power into x to the power 4 by 5 minus x critical to the power 4 by 5. Okay. Now, this relationship, whatever I said, now combining these two, the above relations, a final relation is proposed for Reynolds number which is proposed, which is delta by x equals to 0.381 Rex to the power minus 1 by 5 minus 10,256 Rex to the power minus 1 for 5 into 10 to the power 5 less than Rex less than 10 to the power 7. So, we got some idea about even applying the momentum integral equations for turbulent flow situations. But as I discussed earlier also, for turbulent flow situation, it is usually the analogy that is being used, fluid friction and heat transfer analogy is used for getting the values of heat transfer coefficient okay, because that mechanism of transport is not very well understood in case of turbulent flow situations, and the theoretical development is really a difficult job. What is being done is that that momentum diffusivity is replaced by nu plus epsilon m, and alpha thermal diffusivity is replaced by alpha plus epsilon h. This is the AD molecular momentum diffusivity plus AD momentum diffusivity, and this is molecular thermal conductivity divided or thermal diffusivity, and epsilon h is the AD thermal diffusivity, and these are the diffusivity terms which are being used in case of turbulent flow analysis, that already we have discussed when we have discussed the analogies. Now, we will apply the approximate analysis. We will try to see by applying a temperature flow, profile also in case in the energy integral equation. So, application of assumed velocity and temperature profiles in energy integral equation. Because we have seen the energy integral equation, we need to put both the equation, both velocity and velocity expression and temperature expression has to be used, and we will make use of a similar kind of velocity and temperature profiles already whatever we have discussed in the last lecture. So, we have taken the velocity profile is V x by V infinity is equal to 3 by 2 into y by delta minus half into y by delta whole cube okay, and T minus TW, TW is the wall temperature, T infinity minus TW, T infinity is the free stream temperature, is equal to 3 by 2 y by delta T minus half into y by delta T whole cube. So, we know that delta is the thermal boundary hydrodynamic boundary layer thickness, and delta T is the thermal boundary layer thickness. So, we have got the two similar kind of relationships already we have seen in the last lecture, that how to get this through use of the boundary conditions. Now, the energy equation that we have developed, that is that d dx of 0 to delta, as which we have also said that how the limit is from 0 to delta T. Delta T is the thermal boundary layer thickness. So, V x into T minus T infinity into dy, and that is equal to minus alpha into del T by del y at y equals to 0. So, now from this I am telling equation 3, from temperature profile del T by del y at y equals to 0, it is coming to be, we can understand from this equation, that is T infinity minus T w into, we have 3 by 2 into as we have done in the previous case, into 1 by delta T. Now, if we substitute this in the equation 3, after substitution, what we have is d dx of 0 to delta T into V infinity into 3 by 2 y by delta minus half y by delta whole cube into again T infinity minus T w into minus 1 plus 3 by 2 y by delta T, okay, minus half y by delta T whole cube, okay, into dy. This is equal to minus alpha into T infinity minus T w, okay, into 3 by 2 into delta T. Now, we will define say two variables, like xi is equal to say delta T by delta is the ratio of thermal boundary layer thickness to momentum boundary layer hydrodynamic boundary layer thickness, and say eta 1 equals to say y by delta T, and then we have V infinity d dx of, now eta 1 equals to 0 to eta 1 is equal to 1, that will be the limit, and delta T into 3 by 2, if we just substitute, just multiplication and then substitution, 3 by 2 xi eta 1 minus half xi cube eta 1 cube into say 1 minus 3 by 2 eta 1 plus half eta 1 cube, okay, into d eta 1 is equal to 3 by 2 alpha by xi into delta. Now, we will replace delta T by delta and putting in the form of xi, then we will get integrating. If we do the integration, we will get that V infinity into d dx of delta into 3 by 20 xi square minus 3 by 280 xi to the power 4, okay, this equals to 3 into alpha by 2 xi into delta. Okay. Now, when xi. The point is now, if when xi is equal to, which is delta t by delta, is less than 1, then Prandtl will be less than 1. So, if xi is less than 1, which is delta t by delta 1, then Prandtl is less than 1, then 3 by 280 xi to the power 4 is much less than 3 by 20 xi square. Therefore, 3 by 280 xi to the power 4 is neglected. So, if you do this neglect, if you do neglect this the right hand part, then it becomes little easier for us to do the analysis. Then what we get is that then we get d dx of delta into xi square, okay. Then 3 by plus 3 by 4 x into xi cube is equal to 39 by 56 into alpha by nu into 1 by x. That means, or we can say that d zeta by dx plus 3 by 4 x into zeta, okay, is equal to 39 by 56 x into 1 by Prandtl number, where zeta is defined as xi cube. So, this is the expression that we get. Now, we can do the integration. This integration has to be done using the with the help of integrating factor. We have to do the integration using the integrating factor, and if we do the integration, so after integrating, we get that zeta is equal to 13 by 14 into 1 by Prandtl plus c into x to the power minus 3 by 4. So, this is becoming this, and c is integration constant. Okay. Now, the question is that zeta is finite at x equal to 0. When x equal to 0, zeta is a finite quantity, and if this is to happen, then c has to be 0, because if we put x equal to 0, so it is 1 by x. If x is equal to 1 by x to the power 3 by 4, if x is equal to 0, then zeta becomes undefined, but this is not the case. Zeta is xi cube, zeta is equal to xi cube, and that is equal to delta t by delta whole cube. So, this is a definite quantity. The ratio of these two should be a definite quantity, and therefore, if we have to have a defined value of zeta under that situation, this terminology cannot exist. Therefore, c is taken to be 0. Okay, that is from the logic, and then what we get is that zeta is equal to xi cube, and that is equal to 13 by 14 into 1 by Prandtl. So, then we can say that xi is equal to delta t by delta, which is the ratio of thermal boundary layer thickness to the hydrodynamic boundary layer thickness, and that is equal to 13 by 14 into 1 by Prandtl whole to the power 1/3, and that is actually equal to 1 by 1.026 Prandtl to the power minus 1/3. So, this is approximated as Prandtl to the power minus 1/3. So, that is what we have already seen, that the ratio of thermal boundary layer thickness to the hydrodynamic boundary layer thickness is normally is equal to Prandtl number, Prandtl to the power minus 1/3, or delta by delta t is equal to, or delta by delta t is equal to Prandtl to the power 1/3. So, this is also we have used previously for some of our understanding, that this is delta by delta t is equal to Prandtl to the power 1/3, and for Prandtl number is equal to 1, delta is equal to delta t. Okay. Then what we get is, once we have got the expression for delta, So, delta t by delta already we have seen is equal to Prandtl to the power minus 1/3, then delta t will be equal to 4 point delta into Prandtl to the power minus 1/3, and that is equal to 4.64, okay, into x. Delta is equal to x 4.64 x by Rex to the power half, and then Prandtl to the power half, 1/3. Okay. So, then this becomes one important understanding for us. Now, delta t we know hydrodynamic thickness, thermal boundary layer thickness, or we can write that delta t by x as we have written in case of hydrodynamic boundary layer. So, it is 4.64 divided by Rex to the power half Prandtl to the power 1/3. So, the difference between this hydrodynamic boundary layer and thermal boundary layer thickness is that is a factor of Prandtl number to the power 1/3. That is the factor which is the making the difference between the two thicknesses. So, as we have seen in different kind of velocity profile, we are getting different kind of such delta t by x we can find out, but point is that in both the equations have been taken of similar form. The temperature profile and velocity profile in the boundary layer have been taken to be of similar form. Okay. Now, what we will do is we will try to define the values of heat transfer coefficient, and we know at the wall of the plate what happens is, so this is the plate and this is the boundary layer. So, if we say that this is the wall heat transfer, so wall heat transfer rate is equal to the convective heat transfer rate in the bulk. So, you can say that wall heat transfer is happening due to conduction. So, at the wall, so minus k into del t by del y at y equals to 0, that is the conductive heat loss from the wall to the fluid in the near vicinity, okay, layer is equal to the convective heat loss, and this is defined as H x into T w minus T infinity. This is the Newton's law of cooling, and this is the conductive Fourier's law of thermal diffusion. So, Fourier's law, which is happening by conduction method of heat transport at the wall, is becoming the Newton's law of cooling, which is by convective mode of transport, and here the area, both the cases the area remains the same. Okay. That is being applied when it is under steady state condition, whatever it is coming into this, that is getting convected away. So, under steady state condition, this is the balance equation, and then H x is basically equal to minus k delta t by del y at y equal to 0 by T w minus T infinity. This is what is the H. Okay. Then we can say that if we put the expressions of this, then H is equal to H x is equal to minus k into T infinity minus T w by T w minus T infinity into we have 3 by 2 into 1 by delta t. Okay. So, then this is becoming 3 into k by 9.28 into x, putting all the values Re x to the power half Prandtl to the power 1/3, and this value is equal to 0.323 k by x Re x to the power half and Prandtl to the power 1/3. Okay. And so, this is becoming, so H x x by k, if we take this is becoming nu x, this is called local Nusselt number, and this is becoming 0.323 Re x to the power half and Prandtl to the power 1/3. So, this is the expression for local Nusselt number, but from exact analysis what we found, is that nu x equals to 0.332 in place of 323 into Re x to the power half and Prandtl to the power 1/3. Already we have discussed this. So, therefore, what happens is we can find out that the expressions from natural number is very close to each other, whether we go by exact analysis or go by approximate method of analysis by assuming some velocity profile and temperature profiles. Now, HL bar, that we know that average heat transfer coefficient for the entire length of the plate, this is given as 0 to L Hx dx divided by 0 to L dx, and this is equal to twice of H at x equal to L. So, average heat transfer coefficient is nothing but for the overall length of the plate is equal to twice of the heat transfer coefficient at H equal to H at x equal to L. So, Nusselt number average Nusselt number is equal to average heat transfer coefficient into L by K, and this is 0.646 in the present case into REL to the power half and Prandtl to the power 1/3, whereas by exact analysis we got Nusselt average is equal to 0.664 into REL to the power half and Prandtl to the power 1/3, that already we have seen. Okay. Now, second point is, so we can see from this analysis that it becomes thermal boundary layer becomes almost close to analysis of the thermal boundary layer gives the things very close to the exact solution case, and exact solution case is becoming very close to the approximate solution case. Okay. Now, there is a possibility that thermal boundary layer starts little later. So, that means that heating of the plate is happening much later. So, if thermal boundary layer starts later, that is the boundary condition is at x equal to x naught only, that delta T equals to 0, that means zeta equal to 0. So, suppose this is a plate, here is the hydrodynamic boundary layer and thermal boundary layer starts from this. So, this is the region x equal to x naught and heating starts from here. There is a possibility, a case, then heat transfer from this angle. So, thermal boundary layer development is little later than the development of the hydrodynamic boundary layer on the plate. Under that situation, this would be the boundary condition, and then we will have zeta is equal to delta T. If we do the integrations properly, this will become Prandtl to the power minus 1/3 into 1 minus x naught by x to the power 3 by 4 whole to the power 1 by 3. Okay. And then we have Nusselt x will be equal to 0.323, Prandtl to the power 1/3 and Reynolds x to the power half, and then 1 minus x naught by x whole to the power 3 by 4 whole to the power minus 1 by 3. Then if x naught equals to 0, then Nusselt x is equal to 0.323 Reynolds x to the power half and Prandtl to the power 1/3. Okay. So, this is what once if it happens like this, then Nusselt number is going to be of this expression, and if x not equal to 0, that means if it coincides to the starting point of the hydrodynamic boundary layer, under that situation Nusselt number again comes back to the original equation. That is what we have discussed. Now, all these expressions and these particularly these coefficients, whatever we have found out, these coefficients, these numerical values are dependent on the kind of velocity profile and kind of temperature profile we are using. And as we have seen previously also that the velocity profile, this 3 degree polynomial, 3 order, third order polynomial is doing better and is performing good, and they are comparable with the exact analysis. So, therefore, we can nicely represent the velocity and temperature profile in the boundary layers, particularly the laminar boundary layer in those forms. But in case of turbulent boundary layer, as I told that that velocity distribution is the 1/7 power law model is used, but particularly for heat transfer, it is usually that fluid flow heat transfer analogy is being used, is normally used to find out the values of heat transfer coefficient. Now, we will discuss a problem. The problem says that in a laminar boundary layer, the velocity and the temperature profiles are given by, say, V is equal to A1 plus B1 y plus C1 y square and T equals to A2 plus B2 y plus C2 y square. What are the using suitable boundary conditions, find the actual velocity and temperature profiles. Okay. So, now if we see that we have for both the velocity and temperature, the polynomials is third order polynomial, and we can see that we have to find out the values of 3 constants for velocity as well as for temperature. So, we need to put three boundary conditions. So, for velocity profile, we will put that at y equals to 0, V x equal to 0. This implies that A1 equals to 0. At y is equal to delta, V x is equal to V infinity. This implies that A1 plus B1 delta plus C1 delta square, that is equal to V infinity, and at y equals to delta, del V x as we know by del y equals to 0. This implies that B1 plus 2 C1 delta equals to 0, or that says that B1 is equal to minus 2 C1 delta. Then we get by substituting B1, we get B1 delta plus C1 delta square is equal to V infinity, and then B1 we know minus 2 C1 delta square plus C1 delta square is equal to V infinity. So, V infinity is equal to minus C1 delta square. This implies C1 is equal to minus V infinity by delta square, and already we know B1. So, B1 is equal to minus 2 C1 delta, and that is equal to 2 V infinity by delta. So, V x is equal to A1 plus B1 y plus C1 y square, and A1 is equal to 0 plus B1 is equal to 2 V infinity by delta plus C1 is equal to minus V infinity y square by delta square. Well, so, we get V x by V infinity is equal to into y. So, we will be getting y 2 into y by delta minus y by delta whole square. So, this is equal to twice eta minus eta square. This is the one kind of velocity profile already we have listed in the previous table, whatever we have discussed today. Now, this is becoming the velocity profile. Similarly, for temperature, we can write at y equals to 0, T is equal to T w, and then we have that T is equal to the T w is equal to A 1, okay, and at y is equal to delta, T is equal to T infinity. This implies T infinity is equal to T w plus B 1 to B 1 y, sorry, this is A 2 T w plus B 2 into delta plus C 2 into delta square, and at y is equal to delta t. So, these are t, delta t, t is equal to del t by del y equals to 0. This implies that 0 is equal to B 2 plus 2 C 2 y. This implies C 2 delta t. So, this says B 2 is equal to minus 2 C 2 delta t, and then T infinity minus T w is equal to minus 2 C 2 delta t square plus C 2 delta t square. This implies that minus C 2 delta t square is equal to T infinity minus T w, or C 2 is equal to minus of T infinity minus T w by delta t square. And then if we know C 2, then we have B 2 is equal to 2 into T infinity minus T w by delta t, and then if we put these expressions, then T is equal to T w for A 2 plus B 2 is equal to 2 into T infinity minus T w by delta t plus C 2 is equal to minus of T infinity minus T w by delta t square, and here it is y, that is y square. So, we got 3 minus T w by T infinity minus T w is equal to 2 into y by delta t minus y by delta t whole square. So, this is equal to twice eta minus eta 1 square. So, this is the temperature profile that we got in the boundary layer. So, this way we can find out the velocity profile and temperature profiles by putting the suitable boundary conditions, and then we can use those in the integral equations to find out the behavior, to find out the expressions for wall shear stress, to find the expression for the heat transfer coefficient, to find out the expressions for thermal boundary layer thickness, hydrodynamic boundary layer thickness, and so on. We can do the calculations. So, this is all about this module of forced convection heat transfer. In the next module, we will start discussing on the free convective heat transfer. Thank you very much.